And now we are going to conclude this section, well, almost conclude this section, by proving a very strong theorem, which is Parseval theorem. Now recall, energy. You have physical space is equal integral 1 over 2 pi, integral from minus pi to pi of f of x squared dx, and frequency space is equal summation of Cn squared from n equal minus infinity to plus infinity. Now assume the following. Assume f is 2 pi periodic, continuous in R, and PC1. Then, from before, we know that the Fourier series of f at x, which is equal to the limit as n goes to infinity of Sn of f, converges to f of x because of continuity. But because of continuity, you know that if it converges on every interval, it will converge uniformly on every sub-interval. But my function is continuous everywhere, so this means that converge to f of x and converge to f of x uniformly. Okay. So let's say, so I have, okay, define or denote Fourier series of f at x to be summation from n equal 1 to minus infinity to plus infinity of absolute value of Cn square, Cn e to the I n x. Yes, this is the Fourier. Now 1 over 2 pi integral from minus pi to pi of f of x squared dx. This is equal 1 over 2 pi integral from minus pi to pi of f of x times f of x bar dx. This is the definition of the absolute value. So this is the energy in frequency in physical space. And this is equal 1 over 2 pi integral from minus pi to pi of f of x times summation from n equal minus infinity to plus infinity by convergence. F is nothing but its Fourier series. Now this is equal 1 over 2 pi integral from minus pi to pi of f of x times summation from n equal minus infinity to plus infinity Cn bar e to the minus I n x dx. And now this is equal 1 over 2 pi integral from minus pi to pi of summation from n equal minus infinity to plus infinity of f of x Cn bar e to the minus I n x, and the whole thing dx. Now your function f is bounded. Why is bounded? Because it's continuous on minus pi pi and 2 pi periodic. So if you multiply it by your sequence, it will, if it converges uniformly, you will stay converging uniformly. It will not hurt your sequence. So by uniform convergence, this is equal 1 over 2 pi summation from n equal minus infinity to plus infinity. I can switch the integral and sum of integral from minus pi to pi f of x Cn bar e to the minus I n x dx. And this is equal to summation from n equal minus infinity to plus infinity. I'll put Cn bar, and then this is multiplied by 1 over 2 pi integral from minus pi to pi of f of x e to the minus I n x dx, which is equal summation from n equal minus infinity to plus infinity Cn bar, but this is nothing but Cn. And this is equal summation from n equal minus infinity to plus infinity absolute value of Cn squared, which is the frequency, which is the energy in frequency space. So when you transmit a signal, even if you transform the Fourier series, you have transmitting not only the signal, you are preserving the energy. And this is, I proved it here for a very specific case, but now I will cite the theorem. So theorem, if f is L2 of minus pi pi, very general, then 1 over 2 pi integral from minus pi to pi of f of x squared dx. Since it's L2, this means this is less than infinity, is equal summation from n equal minus infinity to plus infinity Cn squared, which is equal by by a formula. This is a formula we proved. And this is where I will use it. A0 squared over 4 plus summation 1 over 2 summation from n equal 1 to infinity an squared plus bn squared. Okay. And as an example, so we showed already that Fourier series of absolute value of x is equal pi over 2 minus 4 over pi summation from n equals 0 to infinity cosine 2n plus 1 x over 2n plus 1 square. The question is now find summation from n equal 1 to infinity, from n equals 0 to infinity 1 over 2n plus 1 power 4, and summation from n equal 1 to infinity of 1 over n power 4. So not only I can use this to calculate I used already this Fourier series to calculate what happened at x equals 0, and I was able to use summation of 1 over 2n plus 1 square. In fact, we can do much better here. So by Parseval, so the proof, well, the solution, Parseval implies 1 over 2 pi summation from minus pi to pi of absolute value of x squared dx is equal a0 square over 4 plus summation of 1 over 2 summation from n equal 1 to infinity an square plus bn square. Now this is a0 over 2. So first of all, if you integrate this one, you will get 1 over 2 pi x squared, so it will be x cubed over 3, it will be 1 over pi times pi squared pi cubed over 3. This is this integral. If you're not convinced, check it, okay? It's a very easy integral to compute. a0 squared over 4 is a0 over 2 squared, which is pi over 2 squared, plus I add the an and the bn. When you add the bn are 0. When you add the an, these are the only one who survive. So this will be plus summation from n equal 0 to infinity, because the 2n plus 1 survive, and you have 1/2 of 4 over pi times 1 over 2n plus 1 square, the whole thing square, and absolute value. But that's it, yes? So you get pi square over 3 equal pi square over 4 plus 8 over pi square summation from n equals 0 to infinity 1 over 2n plus 1 power 4. What I did here, if you're not sure, bn is 0 and an is 0 when n equal to k, and is equal to what? 4 over pi blah 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 for n equal to k plus 1, where k is 0, 1 thing, and then this is the one that survives. You put k and then you replace k by n. So this implies summation from n equals 0 to infinity of 1 over 2n plus 1 power 4 is equal pi 4 over 96 So what about summation from n equal 1 to infinity of 1 over n4? We already saw this. This is summation from n equal 1 to infinity of 1 over 2n power 4 plus summation from n equals 0 to infinity 1 over 2n plus 1 power 4. This is the odd and this is the even. We already saw this. So you get pi 4 over 96 equal 1 over 2 power 4. I put the 2 power 4 outside times pi 4 over 96. No, sorry. So summation from n equal 1 to infinity 1 over n4 equal 1 over 16. Summation from n equal 1 to infinity of 1 over n4. And I know that this is equal to pi 4 over 96. You bring this to the other side, and you get summation from 1 to infinity of 1 over n4 equal pi 4 over 90. In fact, it's pi 4 over 96 times 16 over 15. But I mean 96 is 16 and 6, so the 16 will cancel and you get this. And the last theorem is the Riemann-Lebesgue lemma, very important theorem. It tells you that if f belongs to L2 of minus pi, then the limit as n goes to plus infinity of Cn and the limit as n goes to minus infinity of Cn equals 0. The limit as n goes to infinity of An is 0. The limit as n goes to infinity of Bn is 0. It's a very important lemma, and it has Riemann and Lebesgue in it, so you should see this. And this is the Fourier coefficient, always goes to 0. But remember, the Fourier coefficient Cn is the coefficient of e to the in x. So it's the part of the signal with high frequency. So the part of the signal that fluctuate fast, their amplitude, where the coordinate goes to 0. Well, the proof is f belongs to L2 of minus pi, then by Parseval summation from n equal minus infinity to plus infinity of absolute value of Cn squared is equal 1 over 2 pi, taken from minus pi to pi, f of x squared dx, and this is smaller than infinity. And this implies that the limit as n goes to infinity of absolute value of Cn squared is equal to 0. This is by nth term test. So this implies that the limit as n goes to infinity of Cn equal to 0. If the absolute value goes to 0, then your sequence by itself goes to 0. But similarly, same thing happened for minus infinity. So plus or minus. But also, so this means this converge, okay? But also, summation from n equal 1 to infinity of an squared plus bn squared is less than infinity because of the formula. I mean, you have the following. This is equal to this. So if this converges, this sum should converge. And now this is one-sided sum. So this implies that the limit as n goes to infinity of an squared plus bn squared equal to 0. But these are two positive sums. So this implies the limit as n goes to infinity of an equals the limit as n goes to infinity of bn equal to 0. So I mean, the Fourier does incredible things. It takes the average, it conserves the energy. If the thing, the part of the signal that fluctuates very fast, it kills them, okay? And so as an example, what is the limit as n goes to infinity of summation of x squared cosine cube x sine nx dx between minus pi and pi? Well, if you put the limit inside, the limit of sine nx does not exist. But I mean, who told you can put the limit inside? I mean, this thing does not even, I mean, you don't know if the thing inside does not even converge, okay? as n goes to infinity. But I'm telling you that the limit is equal to 0. And why is that? X squared cosine cube x is continuous on minus pi pi. Then x squared cosine cube x belongs to L2 of minus pi pi. And this implies that b sub n of x squared cosine cube x, which is equal to 1 over n, and this is Riemann-Lebesgue lemma, integral from minus pi to pi of x squared cosine cube x sine n x dx goes to 0 as n goes to infinity. And that's the proof. Okay, so that's the end of this part. You should spend a lot of time on today's lecture. Okay, you should give it a lot of time. You should give it a lot of thoughts, and let me know if you have any questions. So the next lecture we're gonna finish the heat equation. Okay, thank you.